Okay, I start a private recording as well as a backup. Okay, maybe we wait a few seconds yet because I see people are still coming in.
Yes.
Okay, thanks. I'm killing it today. Everything works. Okay, so maybe we can start then. So welcome back everyone to this session of the One World Priority Seminar on branching processes forward and backward. And the first speaker today is Sandra Palau from UNAM that will talk about, I guess, the forward part of the branching processes forward and backward in varying environments. So please go ahead.
So thank you very much to the organizers. This is part, so what I'm going to present is part of a joint work with Natalia Cardona from CIMAT and part of a work in progress with Simon Harris and Juan Carlos Pato. All the simulations that you are going to see were made by Enrique Moctezuma from UNAM. So what we wanted was to see or construct the genealogy of a sample taken in the future in a branching process in varying environment. So what is this? Well, we are going to work with Galton-Watson processes in varying environment. So these are branching processes where the reproduction capacity of individuals might be affected by the resource supplies or the weather condition, as in this picture. So then all the individuals in the same generation will have the same offspring distribution, but they can change or vary among generations. That is what we are going to call varying environment. So more precisely, a varying environment will be a sequence E equal to Q1, Q2, and so on. And it is a sequence of probability measures on the natural numbers that includes the zero. So a Galton-Watson process in varying environment that we are going to denote it short by GWVE is a Markov chain set N defined precursively in the following way. We start with one individual, set 0 is equal to 1, and then set N will be the sum from I equal to 1 up to set N minus 1 of XIN. So here, the XIN will be independent random variables. All of them will have distribution QN. And this will represent the number of children that individual I in generation N minus 1 gives to generation N. So here, then the probability that individual XIN has exactly K children is equal to QN of K. So in my picture, I start with one individual, and this one gives birth accordingly to Q1. So in this case, it gives birth to 3 children, and then each of them that are in generation 1 will give birth accordingly to Q2. So in this case, the first one have 1 child, the second one doesn't have, and the third one have 2 children. And we continue in this way. So what happens in the constant environment case? So here we have a simulation. In this case, all the offspring distribution were linear fractional. That means that we have 2 parameters, A and B, that are between 0 and 1. Actually, it can be A equal to 1. And we have that the probability that my individual doesn't have children is 1 minus A. And if decides to have children, that is this A, then it will, the number of children that is going to give is a geometrical random variable with parameter P. So that is it. And here we have different behaviors. So in the first behavior, in this case, when A is less than P, we are in the subcritical case, and that means that we will have extinction almost shortly, and the extinction is quite fast. In the second case, here, when A is equal to P, we are in the critical regimen, and in this case, we will have almost shortly extinction, even that in average, we have one child per generation. So it will also extinct, but like we will see like in this form. And finally, when A is bigger than P, we are in the supercritical regime, and that means that we can have extinction, but in the places that we don't have extinction, our process will grow up exponentially fast. And you can see here, we start with one individual, and quite fast, it has a lot of individuals. And what happened with the varying environment case? Well, in my simulations, we also have a linear fractional distribution, but in this case, at every generation, the AN and PN can be different. So here, what we have, in some cases, we put AN bigger or smaller than PN. In other ones, we put AN equal to PN, so we don't know. And as you can see, it's not easy to know what is going on with our process. No, we have these funny shapes. Sometimes you think that it will die, but at some moment it starts to grow up. Or you can see like these funny shapes. So an interesting question is what is going on with this process? Can I say if I will have extinction or not? So let me tell you some basic properties. So first, if I want to know the generating function of the population size at time n, that it is this exponential of s to the set n, then we can prove by using the branching property that it is the composition of f1 with f2 up to fn of s, where here the fi's are the generating functions associated with the environment qi, that it is how individuals in the I-1 generation give birth. So if we differentiate 1 and twice, we can obtain the mean and the second factorial moment of our population. For the mean, we can see that it is the product of the means at each generation. And we are going to call that mu(n), and mu0 is equal to 1. And for the second factorial moment, we can see the same. We can see that it depends on the first and second factorial moment of all the generations. That it is this part of here. And I'm going to denote by rho n, the second factorial moment of the population at time set n. So then, Kirsten showed that under a mild condition, the probability of survival has the same behavior as 2 times this fraction. And here at the top, I put what we already call the mean and second factorial moment. As you can see, this part, it is the inverse of this series, right? And moreover, he showed that the process will have extinction almost surely if and only if in mean we goes to 0, that means that the limit of mu(n) is equal to 0, or that series, that is the same one as this, goes to infinity. Then the inverse will also go to 0. And if one wants to know why this is, well, we know that if these two things are satisfied, then we will have almost surely extinction. If one of them is not satisfied, sorry, if the two are not satisfied, we will have that with positive probability, we have survival. And what we want to do is to find a good phase transition, like in the constant environment case. We want to see what it is critical, that it has to be something that we will die, but in average, we will have a mean, positive mean, right? So Kirsten also found this, and he defined that something, we are in the critical case if not only we have that the series is infinity, but also the limit when n goes to infinity of mu n times the partial sum goes to infinity. And why this is a good phase transition? Well, he showed that under this extra assumption, if we take the limit of the mean of the process conditional on survival, we will have that limit is infinity. And without this extra assumption, we will have that limit is finite. So natural question is if there is a sequence AN such that set n over AN conditioned on survival converge to a random variable. So the answer is yes, there is, but we will have to find the AN and also we have to find the random variable. So in order to find the AN, well, a clue, a key point is to find this mean, this condition and mean. So what is going on with that? Well, if we take that condition and mean, remember that is the original mean over the survival probability. So the mean, we already know that it is equal to mu n. And the survival probability, Kirsten showed that behaves as rho n over 2. So a natural factor that we can define it is this one, right? Because at least if we put a n equal to mu n rho n over 2, the mean will converge to 1. So we know that the conditional mean converged to 1, and now we have to find what is the distribution. So Kirsten and also Natalia and me show that if we have set n a critical Galton-Watson process in varying environment, then under the same mild condition of Kirsten, set n over an conditional on survival converge in distribution to a standard exponential random variable. And something about this was that Kirsten showed this convergence in an analytical way. So he proved that the Laplace transform of this process converged to the Laplace transform of an exponential random variable. With Natalia, we did it in a different way. So we use to explain the composition. And I'm going to present this at the end of the talk as an application of our genealogy. Okay, so remember that I said that we want to see the genealogy of a sample in the future in our process. So what is this? So we are going to work again with the critical case, and we are going to suppose that until time n, our process has survived, and we are going to choose k particles uniformly from those that are alive. And our question is, how does their ancestral tree looks like? And what happens when n goes to infinity? So here we have some simulations. In all of them, we are in the survival event. And we select, I think that in all of them, I select 5 particles. In this case, we only have 4. And as you can see, we have different pictures. Sometimes it is like quite thin here and then go big and then again thin. Other one we have like this fish shape and we have like different faces. So we want to know what is a picture of this when n goes to infinity. So in order to do that, first I need to explain something about rooted trees. Okay. So we are going to work with the Euler-Harris labeling. That means that we think we have the empty set and we will have vectors or finite sequence in the natural numbers. This one doesn't include 0. They have to be bigger or equal than 1. So for an element there, it can be the root, sorry, the empty set, or it can be number sequence U1 up to UN. So we are going to denote the length. So if U it has this form, the length will be N, how many numbers I have. If I have the empty set, its length will be 0. And for an U in U, we are going to call the genealogical line this set. So it is conformed by the empty set, and we are going to add all the vectors of the form U1, U2, UK for every j between 1 and n. For two vectors U and B of the form U1, UN and B1, BM, we are going to call the concatenation, denoted by UB, as just the product. I put first U, U1, UN, and then the next part of the vector, it will be B1, BM. So in my example, if I have U equal to 1 to 3, then the length is 3. And its genealogical line, it is conformed by empty set 1, 1, 1, and 1, 2, 3. If I have this extra vector B equal to 3, 1, then the concatenation of U and B will be 1, 1, 2, 3, 1. Okay. So now that we have that part, we can define what it is a rooted tree. So a rooted tree that we are going to denote it by T is a subset of U such that satisfies 3 conditions. The first one is that all of them will have the empty set. And if I have an element U in my tree, its genealogical line will also be in OR3. And finally, if I have an element in my tree and I have an I in the natural numbers, including 0, such that UI is, well, sorry, it doesn't include 0, such that UI is in OR3, then UJ has to be in OR3 for all j less or equal than I. Okay, that is a rooted tree. And for every element in my tree, U, we can define the number of offspring of U by LU, that it is the maximum I in N0 such that UI it is in OR3. And we are going to call leaves the element that doesn't have offspring. That means that the B's in my tree such that L of B is equal to 0. And we are going to call spines the genealogical lines of the leaves. So in a picture, something like this, well, we have that tree. We start with the root, that it has one child, the 1. Then the individual 1 have 5 children, 1, 1, 1, 2, 1, 3, 1, 4, and 1, 5. Individual 1, 1 have 2 children, 1, 1, 1, and 1, 1, 2. Individuals 1, 2, and 1, 3 doesn't have child. And individuals 1, 4, and 1, 5 have 1 child, each of them. So 1, 4, 1, and 1, 5, 1. So here, if I select individual 1, 1, this is its genealogical line, empty set 1, 1, 1. And here in the rest of my talk, all the individuals that have at least 1 child, I will put them with black. Yes. And all my leaves will be put in color red. So here, individual 1, 2, 1, 3, 1, 1, 1, 1, 1, 2, 1, 4, 1, and 1, 4, 5 are leaves. And for example, this one is a leaf. So this red line is a spine. The empty set 1, 1, 4, and 1, 4, 1. Okay. So now that we know the rooted trees, what we want to define, it is a rooted tree in varying environment condition that has with K spine. So how are we going to construct it? Well, we will start with one particle that have K marks, and then all the particles in generation M will give birth accordingly to Qm plus 1. This is because we want to have a Galton-Watson tree in varying environment. And then if a particle has J marks, and give birth to C children, then the marks will choose uniformly from the lines to follow. In my picture, I start with one individual, this one, the root, and it gives birth accordingly to Q1. And in this case, it only gives birth to one individual. And this root has 4 spines. Since I only give birth to one individual, the 4 spines goes to this individual. Then this individual gives birth accordingly to Q2, and it gives birth to 5 individuals, and then the spines of the marks move uniformly from all of them. So one of them goes to this point, and 3 of them go to the first children. And here again, this new individual gives birth accordingly to Q3, and from the 2 children that it has, the marks move uniformly. And in this case, since this individual didn't have children, then the marks stay there. So now that we know how to construct our process, what about the distribution? Well, we are going to work, so our state space will be trees with K spines, and we are going to call a Galton-Watson tree invariant environment E with K spines a TK value random variable that has the following distribution. The probability that our tree up to generation n is equal to a given tree and spines will be this product. So in this product, the first part, this one, has everything to do with how I select the tree, right? So I need that every individual in my tree have exactly L of U children. And remember that the offspring distribution depends on the generation. That is why we have Q of the length of U plus 1. So this part is how I select the tree. And then I need to select the spines. So the spines will be selected in this form. So remember that we say that from the children that you have, we select uniformly which one or in what place we move. And that is why we have this 1 over L of U. So what happens with the picture that I have before? What is the probability of obtaining this specific tree? Well, the first individual, it only have 1 child, and that I have it with probability Q1 of 1. This individual has 5 children, and I have that with probability Q2 of 5. This individual has 2 children, and that is, I have it with probability Q3 of 2. These 2 individuals didn't have children, so that is our Q3 of 0 squared. And finally, these 2 individuals didn't have 1 child, and that is our Q3 of 1 squared. So that is our tree. And what happened with the spines? Well, since I only have 1 possibility here, all the spines move to the same point. That didn't appear here. But in this part, this individual has 5 children. So then the spines have to choose between all of them, and I have 4 possibilities. That is this 1 over 5 to the 4th. Since this individual didn't have children, I stopped there. But for the top one, it has 2 children. Then the 3 marks that I have in this position, they have to move uniformly, and that is why I have the 1 over 2 to the 3. But observe here, we have that the spines or the leaves, I can choose them from individuals that were already there, they didn't arrive at the end position, right? So this individual is not in N, it already died before, well, in genealogical line. Or I can also select 2 times the same span. But what we wanted was to select K different particles and to see the genealogical tree. So then I want to avoid this thing here. So in order to do that, what I'm going to perform, it is a change of measure. So then I need a function g over this function, this state space. And my function g is the following. This one. So g of a specific tree and spines, we are forcing, in this first step, we are forcing that all the spines are different. And here, we are forcing that the spines arrive up to generation n. And finally, with this last term, we are selecting uniformly from all the individuals alive in the present generation. So in my picture, remember that the black dots were individuals that have at least one child, and red dots were leaves. So we are going to select our spines only from the blue ones, and we are going to select the K different. Okay? So if we perform a change of measure using this G, this gives us a measure where we are selecting K spines uniformly from all the different alive individuals at time n. So using this Qn of K, so what are the properties? Well, the first one is that if I denote by x of k, the k factorial of x, that means that it is x times k, x minus 1 times x minus k plus 1. Then set m from m less or equal to n on the measure Qn of k is actually the set nk factorial size bias transform of set n. Conditional on survival. What does that mean? It means that for every bounded function f, this equality it is satisfies. And I'm going to use this part at the end of my talk. Okay. So that is one. But we wanted to know, remember, we want the genealogy of a K sample. So we are going to denote C1, C2 of CK, the spine splitting times. In other words, Ci will be the time where the ith spine is created. So in our picture, we can see that sometimes there are the same time as here. We have that C1 is equal to C2, and other times they are different. So we want to know how does C1 up to CK minus 1 behave under Qn of k as n goes to infinity. And moreover, we want to know that in the splitting times, how many new spines appear. And with these two things, we can characterize the shape of our genealogical tree for our samples, right? It is enough with this. So, but something important is that if we are working with up to generation n, the case will be changing from 0 to n. And this is quite difficult to take care of that. So what we need to do is to perform a time scaling. So instead of working with generation 0, n, we are going to work with points in 0, 1. And how we are going to perform this time rescaling? Well, remember that we define rho m as the second factorial moment of a generation n, that it was given by this partial, this sum from I equal to 1 up to n minus 1 of this fraction. Okay? So for any t in 0, 1, we are going to denote by Sn of t the generalized inverse of rho m over rho n, where here it is the inverse. It is fixed the n. In other words, our set n of t will be the minimum of all the m's such that rho m over rho n is less or equal than t. So I have a picture here. We have this tree, remember red dots are leaves, and under our time rescaling, Sn of t, we obtain this tree here. And something important and good to note, it is that generations that has a lot of leaves, that means that we will see a lot of red, are pushing away the next generation, as this one. Is this pushing away? And generation that have a lot of blood, they are like almost collapsing with the next generation. And why that is this happening? Well, if I have a lot of leaves, that means that my second factorial moment is quite big in comparison with the other generation. That is why we are obtaining this kind of behavior. Okay, so now that we have the time rescaling, well, with Juan Carlos and Simon, we prove that under the time rescaling or splitting time C1 up to CK, here you can see this time scaling, under Qn of k converge to a k-1 order sample of 0, 1 uniform random variables. And moreover, in the limit, under Qn of k, any splitting time will be always, it will appear only 2 new spines. Okay, so this is quite nice. We have the Qn of k, but what we wanted was under our original measure p. So in order to do that, it is easier to work not with the ordered sample, but with a random permutation. So we are going to denote by C1 tilde CK minus 1 tilde a random permutation of our CIs. And what we show is that under our original measure, the CIs converge to a vector that has this distribution. And something important here is that this is the same limit as Harris, Johnson, and Robert obtains for the constant environment case. And what it is like a K point, it is the change of the time rescaling, right? Because what we are doing with the time rescaling is like we are moving our process in such a way that it is almost a constant environment process. That is what we are doing. And this complements what Karsten did this year. And he showed that set with the same time scaling for conditional on survival converge to a Joule process that also perform a time scale. Right? So here he's showing for all the process, and what we did is to have a selection of points, a sample, and then see the tree. And now I want to show you some pictures, some simulations. So in all of them, we have 4 spines, and we are changing the environment, the generation. So we start with 10 generation, 20, 30, and so on. All of them are seen with the time scaling, and we fix the seed in the simulation so we can see how the environment is affecting the process. So as you can see here, we have this funny, well, triangle shape that it is here. And then it will be smaller and smaller. Right? And something also that we can see is that the spine will be the same until the time where that spine dies, and then we will select a new one. So you can see that. And this is more simulations where we have n equal to 70, 85, and 100. And here below, what I put is the same process with the same seed, but without the time scale. So as you can see, we always have these gaps, but there, since our process is critical, in the limit that gaps will collapse and will be smaller and smaller, and we will see almost like the same picture, right? So this was our case sample, and we already know everything about the genealogical tree. And now for the rest, or the last part of my talk, I want to give you an application of this and how to use it in order to prove Jaglom limit. So Jaglom limit was that our process over AN conditional on survival converged to a exponential random variable. So in order to do that, as I said, we were going to use a two-spine decomposition. So let me denote that set n dot or process set n, both with the measure qn1. That means that our tree will have one spine. And I will denote by set n double dot or process under qm of 2. That means that our tree will have two spines. And here something that we have to remember is that set n dot was the size bias set n size bias transform of set n, and set n double dot, it is the set n times set n minus 1 size bias transform of set n. So if we want to know how many individuals I have at generation n of our tree with two spines, we can decompose it in how many individuals are attached to the longer spine and how many individuals are attached to the shorter spine. And here, well, for this one, I don't have a problem, right? Because it will be a set n dot and the environment is the same one, and I move the same quantity of generation. But for the shorter spine, that it is this one, our environment starts in a different position. It starts here, that it is cube c plus 2, cube c 1 plus 3, and so on. So then I put here just to remember that our environment are changing. So the total mass here, it will be set dot. It's a tree with one spine, but we start with environment E C1 plus 1, and we only need to move n minus C1 minus 1 generations. Okay. So for a moment, suppose that set n over an conditional on survival converge to a random variable that we don't know what it is. It's this y that it is unknown. Since set n dot and set n double dot are the size bias transforms of this one, then set n dot over an has to converge to the y bias transform of y that I'm going to denote it by y dot, and the same has to happen with set double dot. Set double dot n over an has to converge to y double dot, and y, where y double dot is the y squared transform of y. So that is in general. So what happens with the decomposition that we already obtained? So we have that set double dot was equal to set n dot plus this set n dot, but it's set n minus c1 dot. Right? So then we divide by an of e, and we know that this first term converges to y double dot. This term here converges to y double dot, and in this part we only have this part, this thing here, right? And the renormalization is bad, so we have to correct it. So we add this extra one, and the last term converges to y double dot prime. And something important here is that by the branching property, how many individuals I have with the longer spine, it is independent of how many individuals I have for the shorter spine. And moreover, we already knew the distribution of CI. So using that, we can prove that this fraction converges to a uniform random variable. Then the variable y that it is unknown has to satisfy this equation, that y double dot is equal to y dot plus a uniform y dot prime, where y dot and y dot prime are independent. And this is the characterization of an exponential distribution. Therefore, our y has to be exponential. And these are the references. Thank you so much.
Well, thank you very much for your talk. I think a round of applause is. So now we have time for some questions. So if anyone wants to ask a question, you can unmute yourself and speak or indicate it in the chat. Well, if I may start, so regarding your results on the process with K-spine, I assume that you need a case moment, right, for the number of children at each generation. You need the finiteness of
yes
of basically all moments, or at least K moments, or something like this.
Yes, actually, you can see that here, right? We need to divide by this one.
Mm-hmm.
Yes.
So, do you know if something similar could be expected if this if the case moment does not exist, or
Yes. So
if the picture becomes very different?
No, you have to put a weight. So no, you don't have to. Your size bias is not. So your G is not only this, but you are affected by an exponential.
Okay.
E to the minus K something. Then you will have that is positive.
Okay, thank you. So I see Sebastian has a question.
Yes. Can you hear me?
Yes.
Okay.
Perfect.
Okay, so first, thank you for the talk. And second, my question, so very naive one, but at the beginning, you gave a formula for the generating function with a composition of F1, F2, up to Fn. And I was wondering if the composition in the reverse order could have some meaning probabilistically or not at all. If we take Fn, Fn minus 1, and we compose in the other order, is this a meaningful quantity or not?
I think that no. How do you obtain this one? Maybe I can tell you. So you just condition it on the previous one value. And remember that your set n is the sum of these x items. Then using that, you will have that it is. So you can think if you are conditioned in the previous one, this you can think it as a fixed number, right? And your x IDs are independent. So then that will be your Fn of S to the set n minus 1. That is why it appears like the composition.
Yeah, okay, and why it's in this order or not the other one, okay. Thank you very much anyway. Thanks.
Yes.
Is there some other question? So question from Zanya Osun in the chat. So does time change make sense in non-critical cases?
Yes, that time change, it can be everywhere. So the only thing is that let me see the time change. If you are not in the critical case, okay, if you are in the critical case, these holes in the limit will collapse all of them. If you are not in the critical case, some of them will not collapse. So then you will have big spaces here that you will not move, and then maybe some of them will go smaller and smaller. But that, you can have it.
Okay, thanks. And maybe if you can ask a follow-up question. So I guess if you had like real world data, so you sample K individuals uniform at time 0, what you get is you don't get the value of the coalescing time in the time change system, but in the original system. So is there a way to recreate the time change from the quantities that you measure in the real world? can you like make an estimator of this change of measure to explain like the history of the process?
Yeah. I don't know. Okay.
I mean, I know Deutsch. Yeah. And yeah, so Anthony, I was asking you about the case where you have like so you don't have those all those polynomial moments. So in that situation, does the result still hold that you have a U-like tree in the end, or can you expect to have different distributions of the times at which the spine split and?
So for that one, under Q, yes, it will be again uniform, but since your G, it is different because you don't have this extra K factorial moment. Here, it will appear something, some e to the minus lambda. Well, I cannot tell you precisely the factor now here, but you will have e to something in this part. But the previous one, yes, it will be uniform. Because that is how you are constructed, right? You are.
Yeah, okay.
Yeah, so this one will be the same, but here you will have overture.
I see. Thank you. So, hello. So, is there some more question? Just let a few more seconds. So, if anyone want to ask a question in the chat or unmute themselves. Well, if not, thanks again, Sandra. So thank you very much for your talk.
Thank you.
And so we meet in 15 minutes, more or less, from for Adrian talk, so at 3 UTC. And I will stop, pause the recording for now.